In previous videos, I went over the RAG pipeline in great detail and also in big picture. So here I'll just summarize really quickly. You start with your query. So say you have some documents that you want to ask some questions on. Those would be stored in your index. They would be in your vector store. And then you submit a query so that you can extract the information that you're looking for. And there's all kinds of techniques for improving your RAG pipeline. I'll just go over the main ones. But you submit your query, and that gets embedded and compared to the documents that are in your vector store using a similarity search or some other algorithm. And then once you have the embedded query, you have a retriever that retrieves the documents that are closest to your original query. Those get retrieved. They're presented here. These are the documents that are closest to in semantic meaning to your original query. They get passed into your generator, which is your LLM, along with the original query, and you're basically asking a question or some kind of prompt on these documents, and the LLM is only using these documents that you've provided to answer the original query. So it's not using any pre-trained information or general information that it was trained on. So you have your response, and that is how you chat with your documents, how you can extract information from the documents that you provide into your RAG pipeline. So in this video, I'll go over how you implement a basic RAG pipeline. In future videos, I'll go in detail on how you can create a sophisticated RAG pipeline with vector stores and different embedding models, different LLM models that you can use, how you can optimize basically for a specific use case. To start, we need to create a knowledge base, and that's the index here. In order to chat with our documents, we need to have some documents stored in an index. But first, we need to install some dependencies. We need to install LangChain. That's the framework that I use in order to build generative AI applications. You can use LlamaIndex. That's another popular one. I just started with LangChain. And then LangChain OpenAI, because we're going to be using OpenAI, their embedding models, and their LLM. Then you need to import LangChain community, and then Face, I don't know how you say it. Face was developed by Facebook, by Meta, and it's a library for efficient similarity search and clustering of dense vectors. And then finally, we need to install TickToken. TickToken is an OpenAI library so that you can create tokens out of your text and use it with OpenAI. So I'm going to run this. Okay, so I just ran this. It took about 16 seconds and the dependencies are installed. I'm going to comment this out, and then I need to reset my kernel. So I will restart it here so that now my dependencies can be used. And here's where I import all of my dependencies. So I will be using OpenAI for their LLM and their embedding models. And then from the LangChain community, I'm going to be installing or importing the text loader. So there are different text loaders, and you can see you have JSON, HTML, CSV. Depending on what kind of documents you're going to be uploading into your RAG pipeline, you would choose a specific one. You could also create a custom text loader. I'm just going to be using their text loader, which is the simplest one. And you can see in their documentation page, this is how you use it. You basically just give it the path to the file, the document that you want to load. And then I'm going to be using a text splitter. And for this case, I'm going to be using recursive character text splitter. So there's different ones. You can look at the options that LangChain offers, but you can split by, if it's an HTML document, you can split by header section. You can split by specific kinds of characters. You can see how they're splitting by the double new line characters, and then they're specifying a chunk size. The chunk size is the maximum number of characters that will be in each split, as long as there's a separator within that split. So for example, if your chunk size is 1000, then your split can have like maybe 300 characters, if there was a separator, in this case it's the double new lines, if within that piece of text there's this separator, then your first split will be less than the chunk size. Say for example you have a piece of text that goes on for more than 1,000 characters before it reaches a new separator, then that split will be longer than your chunk size. So the chunk size really is just like a maximum number of characters that you would ideally want in each of your splits, so long as there's a separator within that text. If your splitted text, or rather the text that you're looking at, doesn't have a separator, then it's just going to continue looking beyond that chunk size, beyond the number of characters, to try to find the next point to split. The chunk overlap is really just the number of characters that will overlap between your splits. So if I were to split up, let's say just this first line of text, if I were to split here, and then the second split would be from the L onwards, then you would want some overlap maybe, so that you can encompass words. So this is a short piece of text, but you can see how maybe in longer pieces of text you would want to have some overlap so that you can capture more semantic meaning. Because ultimately, when you're splitting these documents, or when you're splitting this text, they're going to be individual pieces of document that will be indexed and stored in the vector store, and they won't carry some kind of semantic meaning for that split or for that chunk, and they will be mapped to the vector store. And so if you were to say take this piece of text and split it, and it were to get split by the double new lines, right? So in this case here, and then here as well, you would have one chunk here, another chunk here, and then a third chunk. If it doesn't split, if it doesn't find any double new lines, I should say, this character text splitter will then will default to just a single new line and then empty space, so that it ultimately tries to create individual splits. But say you're splitting this piece of text right here, and for some reason it's split right here. So your next document would contain the rest of this text, and maybe that doesn't make sense. And so you would want to have some overlap so that the first one has the chunk size that it determined to be a good chunk size to split on, and then it will, depending on what overlap you gave it, it will add more characters to that first document, and then for this, in the same way, for the next split, it will take characters from the previous document, from the previous chunk, and prepend it, and also append any characters from the next chunk. And there's different character text splitters. This one we're using just for the example to keep it simple, but there are much better ones. There is one for semantic chunking, where when you give it a piece of text, it tries to identify the semantic meaning of each sentence, and then it will determine if the next sentence has a close enough semantic meaning to the previous one, and if it does, then it groups them together, and it continues iterating through that until it finds a point where the following sentence doesn't really match with the preceding group, and so then it'll create a split there, and then it'll start a new document and continue searching through the rest of the text so that it groups sentences based on their semantic meaning. That's a little bit more advanced, and I'll go over that in a future video, but for now we're just going to be using the character text splitter for simplicity. And then of course we're going to be using OpenAI's embeddings. So we need to embed our documents, right? We have the documents that we're going to be loading. So we've already covered the document loaders, and then the text splitters. Once we have those chunks, then we provide them to the embedder model, and for that we're going to be using OpenAI, and that's why we imported LangChain OpenAI. We imported their embeddings. And for our vector store, we're going to be using Feist. That's Meta's vector store, so that we can load and store these documents locally. When you're building an application, you would want to have your documents available in the cloud, so you would be using a vector store by a vendor. I've used Google's vector stores. It's called Vector Search. There's many out there. It's not just the big companies, but some lesser known companies that have their own vector stores that you can use. But for this video, we're going to be using Feist because it allows you to store things locally. And then from LangChain Core vector stores, we're going to be importing Vector Store Retriever. That's the components right here that's going to retrieve the relevant documents from our vector store given an input query. So to start, I need to load my OpenAI API key. I'm going to do that offline because I don't want you guys to steal my key and then run me up a huge bill. Okay, so I've ran it and my OpenAI key is available in my environment. And one correction I had to make was the import is actually OpenAI like this. And the document that we're going to be loading is a transcript from one of my videos. So I took the transcript from RAG and Big Picture. I didn't take the one from YouTube because that uses Google's transcriber model, and it's not as good as OpenAI because it doesn't provide punctuation. I'm sure you can configure it to do so, but I found that OpenAI's Whisper model was a lot better at transcribing, getting punctuation. And if you're going to be splitting a document by its semantic meaning, then you would need punctuation in order for it to identify individual sentences. So I have that document here. This is the transcription from that video. I go ahead and load it, so I have to run this, and then I'm going to define my text splitter. So I'm using recursive character text splitter, and I'm going to say my chunk size, I want to keep it simple, so I just want to say it's 500, and it does have new lines, so it will be able to split this text. And I want to say I'll have an overlap of, let's just keep it at 10%. And so I'll run that. And before I run that, I have to correct this typo here. I run it. And the length function is really just a callable function that you can define. You can customize it, but it's just how you measure the length of your chunks. And I just want it to be by the characters, so that's how I defined it. And the next thing would be to create the embeddings. So here I am initializing the OpenAI embeddings model. And then I'm going to create my index using FAISS from the document that I've provided. So I named it document up here. So I'm going to be providing it with these variables. I wanted to create an index from the documents, and I'm going to be using this embedding model in order to embed those documents in the vector store. So we're here. We selected the OpenAI embedding model, and then it will convert those to embeddings. And that didn't work because I had to correct the spelling. So if I actually have to run this part again, so it imports the right one, and then I can run this. So it's creating my index using those documents, and it's done. And it's creating them locally, so that's why it's pretty fast. But as you scale, you're creating the index and updating it with more documents does take a little bit of time. I had to close the blinds because the sun was getting in my eyes. Now the next thing, we have our documents loaded into our index. So we have the vector store built, and we can begin to ask some questions. Before I go on, I actually noticed that I had made a mistake when I was talking about the recursive character text splitter. So this one's the recursive one, whereas the other one was the regular text splitter. And it's the recursive character text splitter that first defaults to splitting by double new lines and then a single new line. And if it doesn't find that, then it splits by white space. And if it doesn't find that, then by any character as soon as it reaches that limit. And then we actually also didn't split the document. So here I load the document, and this is just going to use the loader to load one document. And that single document is going to be loaded into just one. So if I were to look at the document's length, then I would see that it's just one document as expected because I'm only loading one. So we actually still have to split it. And in order to do that, we run the text splitter, we split documents, and then we provide the documents they want to split, which is just one. And then I can take a look at the document that it's split it into to see how many, and it split it into 107 based on these parameters that I provided. And then I have to, because I made the mistake of just loading one document and then providing that to the embeddings, I need to rerun this again, make sure that we're getting embeddings for the right documents, which is the 107 from here, not the single document. So it's good I made the mistake because you might end up making the same mistake, and you can identify what the issue is. And the issue was that I didn't split the document. So now I've created my index with the 107 documents that were split. And now that we have our documents loaded into the vector store, we have them here, the embedding stored in the vector store. We can retrieve the documents that are similar to the input query. Directly, we don't need the retriever for that. We can just run a command to execute on the vector store if we want to do a similarity search, because that's ultimately what the retriever does. It pulls the documents that are similar to the input query by semantic meaning. I can do a naive similarity search in the vector store. I just have to define my index, and then I do a similarity search using the query, and I have a list of queries here that I've provided. If I run this, it will give me my similar documents. So this is not the answer to my query, it's the similar documents, and I'll just rerun it so that we can take a look at those similar documents. You can see that there's 4 documents that were similar based on the semantic meaning. My initial question, what is RAG? And the first document, the most relevant one being at the top, it extracted this piece of text. In this video, I'm going to give a general overview of RAG. That's the retrieval augmented generation. So just with that single document that it pulled from the transcript, we could provide just this single document to an LLM and ask it, hey, using this document, answer this question, and it'll be able to answer it because it did retrieve the right one. We have the documents that were pulled, and these are the top 4 documents that are closest in meaning to the original query. If we want to see the score for these documents, then we would use this method here, similarity search with score on our index. And again, we're just running commands directly on the vector store. We're not using the retriever yet. So if I wanted to get the documents and their scores, I can view those documents here. And this is the score that was given. So the closer to 0, the more similar it is. And you can, as you're building out your RAG pipeline, you can see this is where you would add a filter. So if you're doing an experiment to see what documents are actually relevant, you might decide that a score of 0.36 is too high and it's not relevant enough. So you would filter it out here and remove that document from what's ultimately provided to the LLM for context. So this was all to show that you can actually run commands directly on your vector store. You don't need the retriever in order to do that. You can retrieve documents from it directly with different methods that are provided by your index. But now that I have my index, I want to save it, and I'll just call it phase index because that's the type of index that we're using. And I have it saved locally. So if I look at my files, I have the phase directory here that has my vector store, and these are already saved locally, so I can continue this project later. And the way I would do that, I would load my index, and then I provide, so I'm loading it from local, and I have to provide it with the embedding model. And then in order for it to load successfully, there's some security flaw, but we're only doing this locally, so it's safe to add this flag here, allow dangerous deserialization to true. That basically circumvents a warning that it gives you when you're trying to load a pickle file that could have some kind of malicious payload. So I'm going to load that index, and I'll call it saved index. And then from that saved index, now we have basically the vector store, and we can create a retriever. So to create the retriever, we just use that saved index and then run the as retriever. So now this is the retriever that we're going to be using to retrieve our documents. Before, we weren't using the retriever, we were just doing a similarity search directly on the index, but this retriever that we have defined is essentially going to do the same thing. When we invoke it with the query, it's going to do some kind of similarity search, and different vector stores and retrievers will have different methods for extracting the most relevant documents from the index. So if I want to run this retriever, then I invoke it with the query. So I'm going to run this, and then I can take a look at those chunks. So these are the chunks that it extracted. As before, these are similar to when I did the similarity search, but now we're using the retriever rather than using the similarity search method directly. So now that we have our chunks, we can provide that to the LLM, and the way we're going to do that is with a retrieval chain. So I forgot to import this one, but basically this is what's going to allow us to create a chain so that we can provide these documents into the LLM along with the query, the prompt, and then get our answer. So I just run that to import it, And then now I can define my RAG chain. I create a chain type using this LLM, OpenAI. And then the chain type is the stuff. And the stuff chain type is basically just going to take all of the documents and stuff it into the LLM. It's going to provide all of them into the LLM as context. And then I have to define the retriever. There is LangChain has their expression language, so it's the LangChain expression language that makes it easy and intuitive. Once you understand it, you can invoke your RAG pipeline very easily, and you don't have to create, you can create chains very easily, but I'll go over that in future videos. For now, this is how we're going to be defining our RAG chain. I run that. Now we have our RAG chain initialized, and now I can invoke this chain. So basically this chain is saying, take in this retriever, which is going to retrieve documents from this vector store, use the LLM that I've provided, and then use the documents that I've provided from the retriever. And these documents, just stuff them into the LLM. That's basically what this RAG chain is defining. So I can invoke it to get my answer. So this is the answer that was given by the LLM. And the LLM is going to respond with a JSON or a dictionary, and it's going to have in the body the query, the initial query that was provided, and the answer. So if I want to view that, just the answer, then I take that and I'm going to put it in a separate window so that I can view it better. And here we are. The answer is RAG stands for Retrieval Augmented Generation, and it is an advanced search engine that allows for customization of document retrieval and generation, reducing token count and cost. And yeah, in summary, that is what it is. So that's the answer for one of our questions, but if we wanted to ask the other questions, I'll just paste on here and then I'll run that. My query is not going to be the second question. What are the limitations in retrieval? And that is something that I talked about in that video. So if I run the rest, it's going to tell me that it doesn't know. So maybe there's something wrong with the documents that it retrieved. Let me just try again. Sometimes, so I ran it a few times, and just by continuing to run it again, I did get finally an answer. And the possible issue that could have been was that when I retrieved using this question, I might not have retrieved relevant documents, relevant snippets from that transcript that could answer the question. So that's one area where I can improve the retrieval model, or it could be because of when I loaded the LLM, I could define a temperature, and the temperature value will determine like how creative it can be. And in some cases, if it's a high temperature, it's more creative, so it will start to hallucinate. If you set it to temperature of 0, then it'll be more deterministic. It's not going to be deterministic. The answer is going to be different every time because it is an LLM, but it will get it close to the same answer every time. So if I take a look at what it responded with, let me just change the viewer. It says the limitations in retrieval are that it can be time consuming and may not always provide accurate or relevant answers. That's correct. The benefits of using RAG include the ability to implement more advanced components into the retrieval process, scalability, and the ability to limit the documents being searched. Yeah, that's true. RAG pipeline is a method of using RAG to search through documents and provide factual answers. If you ask an irrelevant question to your RAG pipeline, it may not retrieve an accurate or relevant answer. And that's all true. Those are things I did say in the video. So there's other questions, but I won't go through them here because I already ran into an issue that I wanted to, which is when the LLM will say it doesn't know. And in that case, it could be because the retrieved documents didn't have the answer to that question, or it could be that the LLM wasn't set up correctly. So those are just some things that you can play around with when you're getting those kinds of answers from your RAG pipeline. All right, so I'll wrap it up here. Thanks for staying till the end of this video. I hope you found this valuable, and if you did, please give it a like and subscribe so that you can see more content like this and you can continue learning with me to build your generative AI projects and any machine learning projects. Thanks.